Okay, now we're going to talk about a type of model called a generalized additive model, which, if you're not familiar with them, that looks a lot like GLM, right? A generalized linear model. The reason for that is they're actually quite closely related. So, generalized additive models, or GAMs, are actually closely related to GLMs. The primary difference being that they allow you to fit a thing called a smoother, and then actually essentially use that smoother as a predictor variable. And the reason this is appealing is these smoothers can be quite complex. Um, they're quite flexible, and there's all these different sort of smoother types for fitting, for instance, temporally autocorrelated things or cyclical things, seasonal things, things like you can fit these smoothers that are sort of, they go across the surface of a three-dimensional sphere. So it's a two-dimensional surface on a three-dimensional sphere, which is good for doing things that have correlations across the surface of the Earth and all this sort of stuff. So GAMs are like GLMs. It's a very complicated, rich literature. We're not going to dig super deep into it. I'm just going to basically give you the general outline here. Again, this is kind of a course is intended to be more about E&M tools and the hypothesis testing it does there, rather than sort of an SDM methods course per se. So essentially the way a smoother works is you've got sort of like an environmental variable here, and then you've got a response variable. And what you do basically is you fit these sort of local functions, right? And so a smoother is going to try and fit like this little chunk of your data with an equation, and then it will add, for this next chunk, it will add another equation, do like a more localized fit here, right? And so it's fitting this somewhat independently, depending on how you do it, of what it's fitting over here. And then it can fit another model to this little bit, or another sub-model, another section of the smoother to this little bit, and then to this bit, and then to that bit. And so you can basically fit these very localized responses here, which means that you can fit these responses across the range of this environmental variable that are quite complex. And that allows you to fit sort of an arbitrarily complex shape if you've got enough data, and which is sometimes appealing and also a little bit, it feels a little bit like cheating when you're first introduced to it, honestly, because you can fit this really complex thing, which is a bit hard to interpret as an estimate of a biological phenomenon, right? Like, what response to an environmental gradient would this actually connote? It certainly wouldn't be a direct physiological response, you wouldn't think. It's got to be some sort of set of interacting factors that would give you a response like this. Maybe there's some biotic interactions, historical biogeography, whatever. But basically what happens when you fit this smoother is you now have this environmental gradient, and then you have what the smoother predicts. And you fit the correlation between what the smoother predicts and your response variable. So this allows us to control how complex the functions can be, because you can, when you're fitting the smoothers, you can tell it how many knots to put in that smoother. That essentially controls the complexity. The more knots you have, the more sort of inflection points you allow the smoother to have. And one of the nice things here is that we can combine smooth predictors with unsmoothed predictors. And that's worth having to think about. So like I said, you look at a smoother like this, and it's like, well, what does this mean in terms of a biological estimate? And there's nothing intuitive that really corresponds to that. That's not, an interaction between a whole bunch of different things. And so it's, at some level, if you get a response function that looks like this, you're going to feel like that's probably kind of unsatisfying as a biological estimate. However, sometimes you want to fit things that you want to factor them into the model without really caring about how they're estimated. So for instance, if you had, say, spatial sampling bias as a function of latitude and longitude, you might want to have that in your model so that you could sort of factor out the effects of it, but you might not actually care why this is what spatial sampling bias looks like as a function of latitude. right? So you can actually throw in these smooth predictors for that are really complex, along with unsmoothed predictors. So you could, for instance, fit a very complex sampling bias function, but still fit a completely linear function of the species response to the environment. And in that case, then this sampling bias function will be fit to space, not to an environmental gradient. So that's one of the things I really liked about GAMs. When I was first introduced to them, I was just like, this kind of seems like, why not just sort of play connected dots on a graph and then call that a model? Because you can fit something that's sort of arbitrarily complex. And as a modeler, I'm not super comfortable with that. However, there is this sort of like, oh, okay, we can make the parts of the model we don't care about so much be super complex, and then make the parts of the model that we do care about be relatively simple and really kind of spend our time worrying about what those responses look like. I will also say GAMs, even within the sort of world of things you actually do care about estimating, sometimes the GAM smoothers can be more flexible in ways that are very useful to us than are, regular sort of polynomial GLMs. Again, this is not a course on GAMs per se. I do actually teach a course that involves GAMs. We spend an entire day on them there, but honestly, if you really want to get GAMs, that's probably a 3 or 4 week course. But there are a lot of different basis functions for building smoothers. So if you wanted to, you could actually use some of the, what do they call the sinusoidal, trigonometric, whatever. Yeah, there's a particular type of GAM smoother that you could actually use to fit cyclic data. So you could actually use that to fit. You could do a GAM that does like this 3-dimensional smoother for spatial sampling bias or spatial autocorrelation. It has a cyclical smoother for seasonality. So if you thought you were more likely to observe your species at one time of the year than in another, like you can fit smoothers that are actually designed for all these different kinds of data, and then fit on top of that a relatively simple response for, say, this response to your species to temperature. They're just incredibly flexible methods, and it's worth exploring these in depth if you're interested in being a modeler.